27, we start off a capacitor and see how complex networks we can just solve the resistance and capacitor contribution and stuff like that. Okay? So today we will just go through chapter 29. And I will try to solve as many problems as possible from this chapter. And hopefully I will upload a couple of more problems on Island so that I know at the end of the semester you will be pretty much busy with all the courses, all the exams and stuff like that. So you will not get enough time, but we will go through the questions all around us. And also the questions I am solving on. I'll try to accommodate as many as problems in the classroom. I solve everything, and hopefully I'll also give some homework. And I will post a solution on Island. So I will give additional questions on Island so that you can. So we were discussing the magnetic field due to current, right? This was this chapter. Magnetic field. We were looking for the sources of magnetic field and the magnetic field produced by a current carrying wire mostly. And from this chapter, there are two things very, very important. One is the Ampere's law, another is Bio's law, right? So Ampere's law is like Gauss's law, right? When you have several, maybe even if you have one wire carrying current, right? Let's say I take several because you need to know how, when you have more than one wire, how to calculate that. So I have wires which are something like infinite length. Okay. Ampere's law, you need to have some kind of symmetry. Same as Gauss. We discussed this. And you just do an Amperean loop, we call them. It's like similar to the Gaussian surface. Instead, the surface we have here loop. And we will be talking about the length of the loop. And you know, when you have the current, this axis, the magnetic field will be current this way. Right? So, for example, you can take any direction for the Amperean loop. Maybe you take the magnetic field in this direction for this case, or you take the other way. Okay, it's fine. And if you have magnetic field this way, I'm just taking the my length element dl is also the same direction. And what does it say? V dot dl is equal to mu 0 into whatever the current going to the loop, right? And we always take whatever is coming out is going into the surface, it's going into the surface because these are opposite. And this is we take as positive, and this take as negative. If you are choosing the direction of the field in this way, if you are taking opposite, you can take the opposite. But just learn one way, okay? So that you don't make mistakes. So your current is going this way, so it will be the magnetic field. And you can just solve any problem which is having symmetry. If you don't have symmetry, you cannot use the Amperean law, you have to use the Bio's law. So we solved one of the example where we had the infinitely long wire carrying current, right? And we just draw, we were asked to find the magnetic field at a point here, maybe you can call it P, or I think I didn't mention that P or something, but you have some point here around the wire, and you have to find the magnetic field, or you have to find the magnetic field around the wires. Everything is the same. And you just draw an Amperean loop like this, right? You have the small element going this way, or this way. This way, this way, this way, this way, this way. These are same thing, right? And you just do V dot dl mu 0 IE. What is the IE in this case? You have I2 coming out of the plane. So you take as a positive, right? And I1 into the plane. I3 also into the plane. Like this plane. That's how the direction should be decided. And this case you have only one I, so the I in will be I, and you have the Amperean loop like this. The vector B and dl are parallel, right? So you have everywhere wherever you look, your B will be like this, and your dl will be along the B. So it should be, and it is uniform. So you take B outside and mu 0 I. And what is this dl length? Don't get mistaken with the area or something. In the magnetic field, we always talk about the length. Okay, so that's why I use the notation L. So what is the length of this loop? 2 pi r, right? So it should be mu 0 I over 2 pi r. Okay, now we will go to the other laws. We will come back to the Ampere's law later with some complicated questions. But let's see how the Biot-Savart law looks like. So the Biot-Savart law when you have any kind of wire, there you have to have, if the wire has to be infinite, you can apply the Ampere's loop and just solve using the Ampere's law. But when you have any kind of wire or any other structure which doesn't have any symmetry, then, for example, you have some wires like this, carrying current wire, right? And you want to find what is the magnetic field around this, some point B or P or whatever. Since I call P, I just say P or something like that. And what you have to do, to take a small element, dl, okay, and see how the dl is having small magnetic field at this point. Let's say this is at a distance, okay. And now it states the small magnetic field should be equal to mu 0 I, the current, whatever it is carrying, over 4 pi dl cross r cap over r square. Okay. The important thing about this law is that this is first time we are seeing something like this. You have a vector cross to a unit vector. Right? I'm not taking the cross product with this vector, but it's a r cap is just a direction of that the vector r. What is dl cross r cap? What is it basically? You have a cross product, right? Side theta, correct? In most of the cases, this r cap, this is a unit vector, okay? Just show the direction of that. Most of the cases, the magnitude of this one will be 1, right? When you have a unit vector, it's having, for example, I cap, magnitude of I cap is 1, magnitude of j cap is 1, right? Or k cap is 1. Like r cap is having the magnitude 1, okay? In most of the cases. Let's see how we can solve the same problem. The Biot-Savart law you can apply anywhere. It doesn't need any symmetry. If it is a symmetry, it doesn't care, okay? But Ampere's law, you need to have a particular symmetry. Let's see solve this problem by using the Biot-Savart law and see how we get the same result by integrating the steps. It's more like the problem whatever we have solved is for find the electric field. So I'll write the problem again. Let's say example of this one, okay? And infinitely long thin wire carrying current I. Okay, so long wire carrying current I. Find the magnetic field. At a distance of x from the wire. So you have, in most of the problems, I will give you the schematic, especially when it comes to the magnetic field. But this kind of problems, you already know the schematic. You solve this to find the electric field. You have an infinitely long wire, right? And you have to find the electric field at some point P, right? So you have the long wire. This is infinitely long wire, right? And then you have some point X from this wire. Okay, and you have to find it. And this is carrying current I, by the way. Just let you know, this is carrying current I. And you have to find, since it is carrying current I, it will have a magnetic field around this wire. And you have to find the magnetic field at a point, something called P or whatever it is. But if I mention that at a point P. If you just assume that there's a point, okay? Now, if this is if you are using the ambient loop, you can just use this loop, right? You don't need specifically use the Biot-Savart law or ambient loop for any of the problem, unless I specifically mention solve using the Biot-Savart. And I don't want to make your life difficult. This kind of problem I will not be asking to solve using the Biot-Savart law. But by solving this, we will learn some new things to solve different kind of problems. Okay. So the reason I'm choosing the same problem to make you understand that this is much easier than whatever we are solving. Okay. And also you can have
Are we given the value of
mu zero value I will be giving. I will be giving. If I'm asking any numerical question, I will be giving you the epsilon zero, mu zero, and any other constants. Okay. Pi already you know it. 3.141592. You can just keep going on with the numbers. So how we solve this? So Biot-Savart we are talking about the small element dl, right? So we have to find a small element somewhere. Okay? This is my dl. Okay? And I want to find the magnetic field created by this small element at point P. So I just take this point. Okay? And I assume that, since this is correct, I assume that this is at a distance of y and this is at a distance of x. And I just see that my vector to the point is r. Okay? And I can apply the Biot-Savart law, which is small magnetic field created by this dl point will be mu 0 I over 4 pi dl cross r cap over r square. Right? And if I want to find the total magnetic field, each of these small element on this infinitely long wire, so I just do integral of B from word to word. So I'm taking this as a 0.0, right? So if that is the case, it's a negative infinity. It should be positive. Okay? Now, what is dl cross r in this case? Sorry, this is db. Sorry. So this is db. This is integral of whatever this one. Okay? Now, what is dl cross p? Dl cross r cap? dl is in this direction, right? The length element is in this direction, right? This is a vector by the way. The length element is going this direction, and your r cap direction is going this direction, right? So you are taking the angle between. When you talk about the dl cross r, you are talking about the dl r sine theta, right? Yes. And this theta is the angle here. Okay? Or you can also do like this. This you can take pi minus theta, right? And what is sine pi minus theta? Sine pi minus theta. Should be sine theta. Okay? So now, and what is dl by the way? You have a small element on y-axis, right? And I can call them like we did for the case of the electric field. We can call them as, since it is on y-axis, I can call this small element as dy. I will mention this is the y-axis, this is the x-axis. You can use any axis. The problem I solved for my convenience, I used this as a y-axis, and that was an x-axis. But if I am giving that solution, you will see a different kind of notations. But doesn't matter what kind of notation you use. Okay, it's just a convenience. If as far as this distance is x, in your expression, the final expression, you have to express the magnetic field in terms of whatever this distance. Whatever the other axis or whatever the length or element or whatever you use, it doesn't make any difference. Okay. Now, so this is dl cross r sin theta, right? So I can write this one dy, right? The magnitude of the small element I choose as y-axis. So I have dy. And what is r cap magnitude? This one, right? It's just a unit vector direction. It just show you a direction. When you take the magnitude of that direction, it's just 1, right? And this can be written. So since it is, this is dy and this is 1 and this is whatever it is. Okay? So you have dl cross, so let's just write dv. Mu 0 I over 4 pi and dl cross, I can write dy sin theta over r square. Okay? Now you can solve this one. You have solved before for the electric field, right? Use the same technique. How you solve this one? You just substitute whatever the dB value there, right? And you have to make substitution for r. What is r basically?
X squared plus y squared.
R is
X squared plus y
square root of x squared plus y square, right? And what is sin theta here? If your pi minus theta is also
X
theta, so it should be
x over
x over
r
x squared plus y squared square root. So you have everything here, right? Mu 0 I over 4 pi dy, right? X over square root of x squared plus y squared. I'm writing like this, half. And over r squared you have, maybe I'll just write dy here so that I can write r here. R is something like x squared plus y squared, square of the square root, whatever they are. Square of the square root will be the same, right? Now I can rewrite this one, mu 0 I over 4 pi, right, into x dy over x squared plus y squared over 3 by 2, right? Now you have to find b minus infinity plus infinity mu 0 I over 4 pi x dy over x squared plus y squared 3 by 2. Okay? So there are several ways to solve this one. We will use the same technique as we use for the case of the electric field. We use the substitution method. What kind of substitution we use? We use trigonometric substitution, right? I hope you are familiar with this. So simply you take the sides, right? You have y, x, and let's say r, and you have theta here, right? So you define tan theta is equal to y over x, and you differentiate both sides. So this will be 1 over cos square theta d theta should be dy over x. right? So dy you can write in terms of this one, x over cos square theta into d theta, right? Yeah, so when you do this trigonometric substitution, you are trying to change this all the values into a trigonometric form. So whatever that x square plus y square over 3 by 2 you have to change to a trigonometric form, right? So what is cos theta here? From this or from that one, the cos theta will be, or cosine theta will be
X over
x over
R.
r, right? What is r basically? X over
X square plus Y.
x square plus y square
Half.
half, right? And most of you got confusion with this one. Just remember that if you cube this function, you will get this one. Okay? So you have this one there, right? So you can write x square plus y square 3 by 2 is equal to x cube over
Cosine cube.
cosine cube theta. So everything is now in terms of theta function or the trigonometric function. That's the idea of substitution using trigonometry. Because you don't know what is the infinity of some value, right? If you want to integrate. So you use the convenient method. Now, if I just put everything here, this equation will become, right? And what are the limits? Just check that. So when you substitute these things, when your y goes to infinity, right? For example, if your y go to infinity, your theta will go to pi by 2. And y go to negative infinity, it will be
Negative.
minus pi by 2. So your limits also changes. Let's say plus infinity theta is equal to plus pi by 2, right? So y goes to minus infinity theta is equal to minus pi by 2. We did this before. So you just integrate minus pi by 2 to pi by 2, right? And mu 0 I over 4 pi, and you have x, just leave the x there, and you write dy instead of dy x over cos square theta into d theta, right? Over, let me say right, x over cos square theta d theta over, I have x cube over cos cube theta. Now I can cancel several of these things. This can be cancelled out. This whole things can be cancelled out with this one, right? So I will have minus pi by 2 mu 0 I. You can take it outside of the bracket if you want. 4 pi cos theta, right? This will go up into d theta. You have one x remaining here, so this will be this. Let me check them. Correct? Your cos cube theta is 1 over something, right? So when you take this one, it will just, if you want to cancel this one, it will just go like that. So this will be remaining like this. Now you can integrate minus pi by 2 to pi by 2 to minus pi by 2, whatever this cos theta into d theta, right? Can I wipe this part out? Right, if you want to take a picture, take it out. Now, because I will not be, see, the reason I just choose minus infinity to infinity is that this is very common, and when I change the limit, for example, minus infinity to 0, the question you remember when I asked for the one of the quiz, or from 0 to plus infinity, I can change this in any way. I mean, I can even put this point at here somewhere, and I can just twist the question. Okay? Just remember that this Biot's overflow is so convenient to use in these cases. Now, let's see how the result comes for this one. Now I'll just go from here. The B will be equal to so mu 0 I over 4 pi, right? Minus pi by 2 cosine theta d theta. What is the integral of cosine theta d theta?
Supposed to be X.
Oh, sorry, on x. What is integral of this one? Sine theta, right? So this will be mu 0 I over 4 by x sine theta. What is sine pi by 2? 1, right? So this will be mu 0 I over 4 pi x 1 minus 1. So the result will be, this will be 2. You will cancel with this one. So mu 0 I over 2 pi x. My point is at a distance of x, right? If I ask you a point R, you just replace this one. Okay. So this is the result.
What's a negative?
This is minus pi by 2, sine minus pi by 2, right? So this will be like this. So this will be 4 pi, okay? This will be 2. So this 2 and this will be cancelled out. So the final result will be mu 0 I over 4 pi, so over 2 pi x. If you want more clear. Take a picture or write, if you are writing it down, that will be the best. Let's go to the next concept. I'm showing now. The problem solving will take a lot of time. Sorry? It is not?
No, I'm saying we still have.
Okay. Now I will have another type of question. We'll solve a lot of problems. I'll solve everything. I'll try to solve all of the problems. So when I ask the question for the exam, so it will be easy for you to understand. Now, I have find the magnet. I have another question. Find the magnetic field created by circular loop of radius r. Okay, carrying current I at its center. So you have to find the magnetic field, circular properties are find the magnetic field at its center. Instead of making the last sentence, I'll make clear the sentences, because if I ask, okay, current carries circular loop at the center, some of you may get confused with whether the current is at the center or. So it looks like this. You have a circular loop, okay, and it is carrying some current. So the current is on the wire, the loop, okay, and you ask to find the magnetic field at the center. What will be the center?
It's radius.
What will be the magnetic field at the center?
Going out to
Which direction it should be? It will not be zero. So you have the wire. The current is going through the wire. If this is the direction, okay, then the magnetic field will be out of reach. If my current direction changes, what happens? It will be going inside. So in this case, I most of the problems of this kind of these things, I will be giving you the direction of the current, so that you can decide the direction of the magnetic field. If I am specifically asking the direction of the magnetic field. Now, the reason I just wrote like this means out of plane, okay? We discussed this, out of plane into the plane, okay? Now, how we solve this one? How you solve?
So how do we know if the question is symmetry or not?
One thing is that I will be giving you some question like infinitely long thin wire. So for sure you know the symmetry. It's symmetry, right? There are two ways to find the symmetry. One is the translational symmetry, another is the rotational symmetry. Right? So when you are drawing an ambient loop, you have, for example, a wire of length L. You cannot use the ambience law, right? Unless you consider this length is infinite. Because when you have the ambient loop like this, right? When you do the translation symmetry, it loses the symmetry, right? But it still holds the rotational symmetry. Similar to Gauss's law. Gauss's law, when you have a infinitely long wire, right? We just assume that there is a Gaussian cylinder, right? And if you move, it's infinite. So you still hold the translation symmetry, and when you rotate, you have the. And for another example, infinitely long sheet. You remember? So when the sheet is infinitely long, right? So you do the translation, you just get the same thing. Or if you do the rotation, you get the same thing. In most of the questions, when you practice the questions, you will just, by intuition, you will already know that. These kind of things doesn't have any. You can use the ambient loop for this one, but this one I really wanted to solve using the Beer subgroup. So all the examples, whatever I'm solving, is using the Beer subgroup. So what will be the, so this is given radius r, right? What will be the small current created by a small element here? Same thing we will do. For example, I have a DL, right? We did this one for the electric field. The same technique. We just assign theta here, and then take a d theta here, right? Remember? And what is the direction of the r vector in this case?
See?
This we are looking at the center. The magnetic field crosses by this one. So the r vector will be in this direction. Right? Right? So what is dl cross r? As I told you, this is the crucial thing about this problem. You have magnitude of dl, right? Magnitude of r into sin theta. And whenever you look for the dl cross the direction of this r, whenever you change the dl, the r will also going along with this, right? So this theta will always be 90 degree between these two. So this will be dl, and what is the magnitude of the r? 1. So this dl cross r will be just magnitude of dl. And what is the magnitude of dl? You have the radius r, and you have d theta, right? So this is the length element. So you can write this one in terms of r d theta. Now you can solve this one, right? So the small magnitude created by this dl element at the center, mu0 I over 4 pi will be dl cross r cap over r square. So mu0 I over 4 pi, right? This will be dl cross r will be dl, which will be r d theta. So r d theta over capital R square, right? You have the r here is the radius, so it will be capital R, right? Now we can solve it. You got the dB. Now you integrate from where to where do you have to integrate? 0 to 2 pi. You have the circular loop, right? So the maximum can go 2 pi. So the magnetic field will be 0 to 2 pi dB. So this will be mu0, 0 to 2 pi, mu0 I over 4 pi, right? R you can cancel r d theta over, just let me write that. So this will be mu 0 I over 4 pi r. You can take r out, sure, because you are only integrating on the d3. So what is this is the simplest problem. So you have mu 0 I over 4 pi r into 2 pi, right? So this will give you mu 0 I over 2 r. So this is your magnetic field created by the whole loop. Okay? So this is how you apply the Beer-Savart law for kind of loop problem. We had this one. So now we'll come, I mean, you can have any shape of the wire. So just remember, when I ask you about the Beer-Savart law, mostly I will be asking the wires in different shapes. Okay? So for that, you should know how you define the small element of the magnet, the magnetic field, and then you should know how to find the cross product between that small element to the direction of the magnetic field. Okay, right. Now, let's do. Sorry?
Will we bring 2D and 3D for this, like the disc and the sphere?
We will have some questions like three-dimensional, but we are not talking about any surface or some other shapes, right? So we only talk about the length element here, the ambiguous loop, the magnetic field created by, even if it is a three-dimensional object. For example, a thick wire. It's a three-dimensional object, right? And in any case, you will be, I mean, the magnetic field will be decided by how the current is flowing through the wire. So, unlike the complexity with the electric field, this is pretty much easier. I will be asking questions for sure, three-dimensional elements like, for example, let's do some problem. Infinitely long, thick wires, right? So you have the thick wires, right? And I'll be asking you to find the magnetic field outside and inside, right? So it's three-dimensional object. Whenever we are talking about the thin wire, mostly we consider this as a one-dimensional, right? Infinitely thin wires, specifically. So let's do a problem. Question. We'll do find the. I think I have some problem. Since you asked, I guess. Okay. But mostly, when you have the field, unlike the electric field, when I ask you about the three-dimensional object, most of the questions will be you can solve by using the ambiguous. Okay, I'll make sure that there is a symmetry for this three-dimensional, so that will be easier. I'll frame a question properly. A thick wire of radius r carries a total current I uniformly through its cross section. Cross section. Okay. Sometimes people use a hyphen here. And then now I will ask you first part, calculate the current density. Okay. And then there is a reason I just ask you first the current density, the magnitude of the current density, of course. And then I will ask you find the magnetic field, find the inside and outside. First part. Second part I'll ask you to find inside. Okay? So how you solve this one? What is the current density? say I over A, or this is just at the whatever the current pass through a cross sectional area, right? That is why I just specifically mentioned this one. It's passing uniformly through its cross section, right? So you have, let's say the solution. You have, for the first part, you have the thick wires, right? And you have the thick wires are carrying current uniformly, right? So you just assume that, you can assume whether it is going in or out, okay? Just make sure that you choose one of the direction. So you have several of this coming out. I mean, or you don't need to do these dots, but to make you more understanding, you just have a current coming through this cross section, okay? It's the same, you just make one circle, that's fine. And it is having a radius of, what was the radius I gave you? R, okay? And the current density you can define, magnitude will be current over the cross sectional area. And what is the current I mentioned here? I. And what is the cross sectional area with radius R for this circular cross section? It's pi R square, right? So the first part is solved. The second part, you see, this is, once you understood the question, it is very easy to solve this kind of. The second part, I am asking you to find the magnetic field outside, right? So B outside. So you have the thick, you have this thick wire, right? You have this thick wire, okay? And this is having a radius R, okay? You don't need to just, this was, the reason I just showed this dot, to show you when it is carrying current, the field is outside. So you have this thick wire. Now if you want to find the magnetic field outside, you just draw a ambient loop, right? This is having, let's assume that this is having a radius of, then you just use the ambient loop. V dot dl should be equal to mu 0 IE, right? And for the case of outside, this will be B into dl mu 0. You have I current carrying this thing, right? So what is this? What is the ambient loop length with R? 2 pi R, right? So this will be mu 0 I over 2 pi R. This is the case when you have outside, or your ambient loop with the radius of R is outside of the wire thickness R. Okay? Now when it comes to the inside, it's not 0. It's going to be a little bit tricky. So there's a reason I asked you about the current density first. So you have this cross section, right?
Should it be like a fraction?
Should be like a fraction of that. Okay? You are having some current, right? And unless you go to the surface, you are not talking about all the current coming through the ambient loop, whatever the ambient loop you decide. For example, you have the inside. So you have this one. So let's say you have a field like this. Okay. Now you want, and this is having a radius of R. This is having a radius. I want to use. This is having a radius of R. Right? And you want to find what is inside. And you can go all the way from here to up to the surface, right? But should be below the surface. If you are at the surface, definitely you will have all the currents included in this equation. So this will be D dot dl should be mu 0 right? So in this case, let's assume an ambient loop of radius r. Okay, so you have the uniform magnetic field through whatever the region you take. That is mentioned there. In any cross section, you have the uniform magnetic field. B L U0 I A. What is I in here? That is the yeah. So you have the I in should be J into A. What is J basically for the whole current? That's the current density, right? I over what is A? Pi capital R square, right? J we are talking about the whole current density. And what is the area, whatever we are talking about? This one, the small one. Pi small r square. Sorry. So this will be, the current in will be I into r square over capital R square. Right? So you can write this one, B. What is this one? 2 pi r. Right? Right?
Yes.
And then mu0 I r square over capital R square, right? This r square and this r can be cancelled out. So your magnetic field inside will be mu 0 I r 2 pi into capital R square, right? Now if I ask you to plot the magnetic field carrying a thick wire, sorry, yeah, the current carrying thick wire, magnetic field at different points from the center to anywhere outside, how you plot it? The graphical plot. Magnetic field, right? I have the surface here, R, and it's going as a function of R, which means I have I should start the magnetic field from this point. I reach this point, and it changes as a magnetic field as a function of something, right? So it is almost linear with this one, right, inside, right? The small r. Then it goes 1 over r. Okay? And what is the, when you have, what is the turning point? When you are at surface, this r will be this r, right? Correct? So that point will be the maximum. This is proportional, okay? B is proportional. This is proportional. And this is the maximum point. Maximum. So this is a three-dimensional problem. And this is all about the ambient things. Then we'll go to a new concept. We have 15 minutes. It's not a new concept, and this is a continuation of whatever we are learning. So far it is clear, right? So now for the Ampere's law, I can have different kind of shapes. This is just, I gave a infinitely long thick wires, right? I can make the thick wires in different shapes. In most of the problems with the current, because current has to have a direction, right, which should flow, and most of the problem I'll be asking based on the wires. Okay, the current we usually in practical purpose we pass through this one, right? But I can also pass the current through the sheets, right? So how you approximate that one, or in your or let's look into a different point of view. Once we did with the Gauss's law and all the other steps, we were talking about creating a uniform electric field, right? How did we create a uniform electric field? We just keep two plates. One is plus Q and another is minus Q, right? And this field will be sigma over 2 epsilon. This also have sigma over 2 epsilon, and this side will be cancelled out, right? This side will be, right? So this will be add up. So you will have get 2, sorry, in this region for the case of electric field, right? So there is way to create a uniform electric field. You just take two infinitely long plates. Ideally, it should be finite length, but we assume that the distance between them are so close that the length or the size of this sheet is so much length. So that's what we did. But how we create a uniform magnetic field? You cannot create a uniform magnetic field by using a single wire, because with a single wire, your field always will be curling like this, right? So if you want to create a uniform magnetic field, you take several wires, right? So how you look the magnetic field with the several wires? Let's assume that you take infinitely long wires, which is basically sheets, right? And you create the magnetic field. This is carrying I current, all of them, and you just say this is infinitely long sheets in all direction, right? Now you find the magnetic field produced by this one. How you look the magnetic field for infinitely long sheet? So we use the same idea of the wires, where we were looking at the cross sections, right? If you look at if you take, for example, this is your infinitely long sheet, right? And you have the wires, like several of these wires through the sheets, right? And if you look from this side, the cross section from this side, it will be looking like the wires will be coming out, right? Right? So it's as simple as that. Okay? So if the wires are coming out, several of the wires are coming out, right? And you have the direction this way. Now, if you look at the magnetic field for each wire, so how the magnetic field look like for a single wire? You have a wire, right? And your magnetic field will be, if this direction, you have curling this way, you have field like this, right? If you have a second wire, what happens? You have another field curling like this, right? And you have a third wire, you will have another field like this, right? So what we do basically to create a uniform magnetic field, we squeeze the wires and keep very close. That's how the sheets are, right? Which means you have this wire here and you have another wire here, another wire here, another wire here, another wire here, like this. And your magnetic field just go like this, right? With this direction. You understood? So you keep the wire so close so that this field will be added up and you just get a field like this. And if you are going much closer in such a way that you just go very closer, you will get a field add up of all of this. Okay? This is how you have to see the sheet. And how you find the magnetic field, the total magnetic field created by such kind of a sheet. See, these are infinitely long sheet. You use Amelian loop, right? So you take this kind of, for practical purpose, I just draw wires in a separate, and this is going infinity in this direction, infinity in this direction, and infinity in this direction, infinity in this direction, right? You have infinitely long sheet. So the infinity in this direction, infinity, so it's a big sheet. And I'm only looking at the cross section this side, so I just see this. Okay? Now, I can have the field going this direction from here. Okay? And I can have, because this wire will have, the field will be like this, right? So I can have field lines going like this. And when I look at this direction, this field will be, right? So you have wires coming this way, right? So if this field is B, this field will be B in this direction, right? So this will be having this direction. You got it? Because if I take a single wire, the field will be B here in this direction and B here in this direction. This is circulating, right? So like this. So if I have that, for all of the wires, I have a uniform field, almost a uniform field, like this, depending upon your surface gradient. and when it comes to the downside, you will have the other direction. And now you have to do, since it is infinitely long, you can just draw an Abelian loop. You should have a loop. Should be completed, right? So you can draw a square loop, and then you just put the direction of the field and just name it as first part, second part, third part. Like in Gauss's law, we just split the closed surface integral into for a cylinder, the side, top, and bottom, right? Similarly, we can split. We did similar problem for in the case of magnetic field when you have a square loop, right? And how you solve this? So this will be B dot dl, right? Closed integral should be mu 0 I in, right? So the crucial part of this one, whenever you are defining a ambiguous loop, when we were solving these kind of cylindrical problems and all these things, we define the radius, right? Remember, when we have the infinitely long wire at a distance of r, we always define the radius. But when you have a square ambiguous loop, you just make the length, okay? And you just have to check number of wires per unit length, L, okay? And you can call them as N. There are N number of wires are coming per unit length L. So what will be the total I in? Whatever the number of wires coming into I, right? So this will be number of wires coming in that particular length should be that. So you have to have that particular length, okay? And then this one you can split into 4 parts. Open integral P dot dl for the first part plus open integral V dot dl for the second part plus third part plus fourth part should be equal to mu 0 n I into whatever that ambiguous loop length. And what is the first part? The magnetic field and the length are parallel, right? So you have this one, and the second one perpendicular, right? This is the direction of the length, and this is the direction of the field. So this will be 0. The third one, you have parallel, right? It's 180 degree. And then this one will also 0. So you have 2 times of B dot dl because they are having the same length, right? This L and this L are same. Should be equal to mu 0 n I into L. And what is the dl here? It's an open integral of only this side, right? We are not talking about the closed integral L. It's just this side. So that will be L, mu 0 n I into L, right? So this will be B L. I'll write this one, mu 0 n I L. And L can be cancelled out, right? So I will get a magnetic field B should be equal to mu 0 n I over 2, right?
Is it 2 and 3 that cancels out, or 2 and 4?
No, it's from 4.
Oh, sorry. Correct. I was just checking in. Should be correct, right? Because this is perpendicular and this is. Okay.
Dot product will always take cos theta.
Sorry?
Dot product cos theta.
Cos theta.
Cross product and.
Yeah. Cross product sin theta, yeah, it's just, yeah. Dot product, just assume that 2 vectors. This is not part of our lecture, but dot product, we are just checking how you have one vector and another vector, how they are projected together. Right? Where they are equal then this one will be maximum. Now, see, you have seen here, when I have a sheet, it depends on the uniformity of the sheet, right? I create magnetic field with some wiggling, right? So this is not a perfect solution to have a uniform magnetic field. People thought about this, how to create a uniform magnetic field using a sheet, and they come up with an idea. You take a sheet, right? And you look at the magnetic field, and if it is, you have any misuniformity in this number of elements you are taking, you will have that much disuniformity in the magnetic field. So what people did, they take the sheet and they fold it. Okay. Now it doesn't matter whether your wires are having any misuniformity. If you take a sheet, not the same sheet, you take a non-conducting sheet, and you take a single wire, right? And you just wrap them. Instead of having a conducting sheet, you take a normal wire, right? And you just wrap them in any direction. It doesn't matter the directions. Like this, right? And you can get some magnetic field inside of this one, right? Just let me draw it. And these things are called solenoid. So you have a cylindrical shape of an element, right? You have the wires going this way and coming out, and then going this way, coming out, the other side, this way, right? So you are passing some current in one direction, and the current is coming the other direction, right? And these kind of things can produce a uniform magnetic field inside. We will check how it is producing uniform magnetic field quickly inside the field. So you have this kind of stuff. Okay? And now we will check how the magnetic field inside of this kind of so-called solenoid, and how it is useful for certain project like nuclear fusion. We'll first see how we create this kind of stuff. Maybe I'll solve some problem with this, then we can just go. Then we will just discuss the importance of this stuff. So, remember, the electric field we created to deflect a charge, right? The uniform electric field we created between two sheets. If you pass any charge, you have the sheets and you have the fields, right? And you have a charged particle moving with some velocity, right? Depending upon the field direction, it will have a force, right? And then it will bend, right? Why are we creating this solenoid? Why we want the uniform magnetic field? Mostly, if you keep a charged particle in a uniform magnetic field, what does it do? For example, you have a charged particle going, or you have, for your convenience, I'll draw the same field. So you have a charged particle moving with some velocity, right? So velocity vector is in this direction, and your magnetic field in this direction. Which direction your force will be? First vector and second vector. So your force will be this way, right? So you have for example, this is your charged particle point. The charged particle will just circulate with that force. So if you have a uniform magnetic field, you can basically store or accelerate the charged particle in the same path. That's the idea people wanted to have a uniform magnetic field. Okay. So now, we create it by using this solenoid. So we have a solenoid, a non-conducting cylinder, okay? And then we just have the wires. In your textbook, you will only see these kind of wires, okay? You will see this. We can have several. So the other side is, just find it, the other side of the cylinder. So it will be like this. Now you have the current passing through this, right? How you find the magnetic field inside? So you have some field. If your current is in this direction, your field will be which direction?
Will be going from right to left.
This one, okay? So your field will be this one. And in the case of electric field, you know, the electric field lines start from the positive charge and end at the negative charge, right? But the magnetic field behaves very strangely because you don't have a magnetic monopole. Means you cannot have a single north pole magnet. As I mentioned in the first class, magnet, if you break a magnet, which is already having a north and south pole, you will get a smaller magnet with north and south pole, right? So the field lines, if it is going this way, it will not end to any other point. You just loop around. Okay? But if you check the charge, the electric field, you just start from this and end it here, right? So we have this one, right? It never go this going back. So this will be depending upon your distance from this one, so it will be having the loop around. Okay, so the field outside will be going this way, and inside will be this way. Okay. Now, how you find the inside magnetic field for this kind of problem? So whenever you have a wire winded like this, you always check the cross section. So the cross section will be of this one through this part. For example, I take this my red cup. Which minute we have? 2 minutes. I'll finish it. Okay. So if you take this region, okay, so you cut it, and you will see that the wires will be coming out like this, okay? And you take a long solenoid, infinitely long solenoid, and then you can use, maybe you'll continue from here for the next class, but you can use the Amberian loop this one. So you just number 1, 2, and 3, and 2, 3, and 4, and you have the field in this direction, right? And outside you have field in this direction, and you can solve it and find the field. This means that you just, if you cut this one, you will have one side like this, you have another side also like this. Okay, just, I don't know how to slice a cylinder, make a slice of cylinder. Right, then you can just find the this one. That's it for today, and we will continue this chapter. We only have one more topic. We'll do a couple of problems from this if we have time. And then we'll do the toroid. Then we'll finish this chapter.